Hi everybody, I am Daniel and welcome to my presentation about detecting snow cover in multispectral images using deep convolutional neural networks. So the aim of this study is to develop a deep convolutional neural network exploiting both spectral and spatial patterns in multispectral optical images to distinguish snow from clouds and snow-free surfaces. The reason for using optical images is the characteristic spectral signature of snow in the optical wavelengths, where however a major challenge is the spectral similarity between snow and both water and ice clouds, which complicates their automatic discrimination. We treated the detection of snow cover as a multispectral image segmentation problem, which requires a labeled dataset consisting of a feature space X and a label space Y. Now, collecting such a dataset is an expensive task, which is also the reason why only a few publicly available datasets exists. Here we have used two published datasets from the Landsat 8 and Sentinel-2 satellites, with a total of around 100 scenes of different spatial size and resolution. These datasets were used to train the deep convolutional neural network. The network architecture we have used is currently one of the state-of-the-art architectures for image segmentation tasks in the field of computer vision and is called an Encoder-Decoder convolutional neural network. The encoder is composed of a series of convolutional and pooling layers, where the number of kernels increases and the image size decreases with the network depth. The decoder is also composed of a series of convolutional layers, but it includes upsampling layers, which resample the features learned by the encoder back to the original input image size. The decoder is followed by a final classification layer and a softmax activation function, which generates class-wise probabilities for each pixel in the input image. So first we have assessed the impact of the different spectral bands on the classification accuracy of the network. For example, here figure 6 shows the overall and class-wise performance of the network when only using the visible spectral bands, where we can achieve an overall accuracy of around 90% on both datasets. Now, when training the network additionally using the infrared bands, we can further increase precision and recall for each class and the overall accuracy to above 90% of both datasets. And here finally are some classified example scenes of the Landsat 8 dataset, with the true color composite on the left, the ground truth in the middle, and the network predictions and corresponding accuracy on the right. And here we can clearly see that the network is able to distinguish snow from clouds and snow-free areas. And finally, we were interested in the generalization ability of the network to unseen data, which is different from the training data. In particular, if we can train the network on Landsat 8 data and apply it to Sentinel-2 data. And this is a domain adaptation problem, where the challenge is to train a machine learning model to be invariant to a shift in the distribution of the feature space from the source to the target domain. For example, figure 9 shows the accuracy of the network pre-trained on Landsat 8 and applied to the Sentinel-2 dataset and vice versa. And in both cases, we achieved an overall accuracy of above 80%. Which indicates a solid generalization to data that is different from the training data. So in summary, we trained the deep convolutional encoder-decoder network for the snow cover detection task in Landsat 8 and Sentinel-2 imagery. And first we assessed the impact of the different spectral bands on the classification accuracy and observed F-scores of around 70 to 80% and an overall accuracy around 90%. And second, we assessed the ability of the network to generalize the data that is different from the training data, and where we observed also similar F-scores, but a lower overall accuracy. So thanks everybody for listening, and feel free to reach out to me in the live chat of this year's ESA Spy Week. See you there.